In this video, we'll be learning about the central limit theorem. But before we talk about the central limit theorem, we need to review what a sampling distribution is. So let's review. What's a sampling distribution? A sampling distribution involves repeatedly taking a sample from a population and calculating a statistic for each individual sample, and then combining that information to create a distribution. So if we were creating a sampling distribution of the sample mean, we would need to take a simple random sample from the population and then calculate the mean x bar for that sample. Then we would plot this information onto a graph. By repeatedly taking samples and doing the same process, we end up creating a sampling distribution of the sample mean. So now that we've reviewed what a sampling distribution is, let's talk about the central limit theorem. What is the central limit theorem? The central limit theorem predicts the shape of a sampling distribution based on the sample size. Specifically, the central limit theorem states that if the sample size n is large enough, then the sampling distribution of the sample mean will be approximately normal. This means that, regardless of what the population distribution originally looked like, if the sample size n is large enough, the sampling distribution will be normally distributed. To visualize the central limit theorem in action, let's use an example. Suppose we are working with a skewed population distribution. If we wanted to create a sampling distribution of the sample mean, we would need to repeatedly take simple random samples from this population and then calculate the mean x bar for each sample. Combining this information and plotting each value into a graph will give us a sampling distribution. If we take a closer look at each random sample, you would notice that a lot of data points come from the main bulk of the population distribution and fewer data points that come from the smaller areas of the distribution. This is because of probability. The bigger the area, the higher the chance of obtaining data from that segment, and the smaller the area is, the lower the chance of obtaining data from that segment. Because of this, it's possible for us to obtain a sample that only contains data points that come from the main bulk of the population, but it's also possible for us to get samples that only contain data values that come from the smaller areas of the distribution. It just might not be as frequent or likely. Now recall that the average or mean is the balancing point of a dataset. X bar represents the mean of a sample and mu represents the mean of a population. If we were to create a sampling distribution, we would need to take multiple samples and calculate the x bar of each sample. So let's do that. For the first sample, if we calculate x bar, it would be around here. For the second sample, x bar could be here. And for the third sample, x bar could be right here, and so on and so forth. Notice how most of the x bars are located near the true mean mu. And this makes sense because a sample that was properly taken, by definition, should be similar to the original population that it was taken from. However, in order to create a sampling distribution, we need to repeatedly take samples and calculate x bar for each sample. And when we do, we would still see that most of these x bars are located near the true mean mu. Some samples have x bars that are further away from the true mean mu, and that's okay. It's bound to happen based on likeliness and probability. But if we take all these x bars and put them together, we get a big pile of x bars, and this is our sampling distribution. Here we can see that the sampling distribution is normally distributed even though the original population distribution was skewed, and this is exactly what the central limit theorem is talking about. The central limit theorem says that if the sample size n is large enough, then the sampling distribution of the sample mean will be approximately normal. But now the question becomes, how big does the sample size n need to be? The general rule of thumb is that we say that it's safe to apply the central limit theorem when the sample size n is greater than or equal to 30. In other words, the sampling distribution of the sample mean will be approximately normal when the sample size is greater than or equal to 30. The magical thing about the central limit theorem is that regardless of what the original population distribution looked like, the sampling distribution of the sample mean will always be normal if the sample size n is large enough. If the sample size is small, the normal approximation won't be accurate because having a smaller sample size can lead to more variability, lack of precision and reliability, and having a smaller sample size runs a greater risk of obtaining unusual samples just by chance. In summary, a small sample size will not produce a normal sampling distribution, and therefore, for sample sizes less than 30, we can't apply the central limit theorem at all. However, it's worth noting that if the population distribution that you are sampling from is already normally distributed to begin with, then the sampling distribution will be normal even with smaller sample sizes. Because of this, many professors or textbooks will allow you to use the central limit theorem even when the sample size is small, but make sure you check with them. In practice, having a normally distributed population doesn't get you off the hook for needing a good sample size, because we know that small sample sizes produce relatively imprecise estimates of the population distribution and in turn, imprecise estimates of the sampling distribution. So more often than not, in practice, it's better to have a good sample size anyways. But for the sake of this video, it's okay to assume the central limit theorem even when the sample size is small, as long as the population distribution is normal to begin with, because it'll lead to a sampling distribution that is normal as well. The central limit theorem is useful for analyzing large datasets because if we know that the sampling distribution will be normally distributed, we can use formulas that are related to the normal sampling distributions to help us interpret data. Now that you have an understanding of what the central limit theorem is, let's do some practice questions. For each population distribution described below, which options would produce a sampling distribution that is approximately normal? Feel free to pause the video so you can work through these questions yourself. Okay, let's go through the answers. Answers C, D, E, and F are the only options that would produce a sampling distribution that is approximately normal. Answers A and B are incorrect. Let's go through why that is. Answers A and B are incorrect because the sample size is less than 30. Since the sample size is less than 30, the central limit theorem can't be applied, so we can't say that the sampling distribution will be approximately normal. Answers C, D, and F are correct because the sample size is greater than or equal to 30. As a result, the central limit theorem can be applied, so we can say that the sampling distribution will be approximately normal. And answer E is correct because since the population distribution is already normal to begin with, the sampling distribution will also be normal even though the sample size is less than 30. If you found this video helpful, consider supporting us on Patreon to help us make more videos. You can also visit our website at simplelearningpro.com to get access to many study guides and practice questions. Thanks for watching.